So, hello, happy to have all of you here. I'm Anna Valtonen, I'm the Dean of the Aalto School of Arts, Design and Architecture, and also in charge of the artistic activities that we do at Aalto University as a whole. And I'm very happy to have all of you here. Like you might, I know many of you are very well aware of it, and some may be new to this environment. So here at Aalto University, we combine technology, science with business and art. So I think this program that we have ahead of us today is a brilliant and excellent example of that. To me, of course, an artistic approach to things is a way of seeing things in a new light, of being able to look at things from a new perspective, maybe challenge what it is that we're thinking and how we're approaching things. And I think a collaboration like this, where we put together not only brilliant experts from the world around us, but also you, who come from different fields, from different backgrounds and so on, is a very good example of what we are all about. And I think the topic that we'll be hearing about today is also one that's extremely enchanting in many ways, and it's also a good example to me of how this way of thinking of the collaboration between arts and technology and science and the old mathematical thinking and so on has developed. Because if I think backwards, say maybe 20 or so years, origami, and particularly mathematical origami, here in Finland, we didn't really have much of it. So I remember going to these obscure bookstores in Tokyo, trying to find books of mathematical origami and trying to translate, and not doing very well at it, to be honest. But you know, it was a sort of starting interest that was there. But now, if we look at the world around us, basic origami has been something that we're surrounded by, if we like. We see it everywhere. We see, you know, small children doing it. We even, last night at home, we had a book called Star Wars Origami, where you know, build these spaceships and now as part of education at universities. So I think this, if anything, is development, and sort of part of the story that more people than just people who are already very into the topic have realized that this is a way of thinking that's becoming increasingly important. And even when we look at many forms of art, last week we were visiting 3 universities in the US, and also had the great pleasure of going to many great museums and exhibitions that were up. And I think that this kind of how should I put it so that it sounds broad enough and not specific, but I mean sort of modular thinking within expression is something that I can see in maybe 50% of the ones that aren't entirely conceptual, which there's a fair amount of. This thinking seems to be gathering more and more foothold. So it's clearly something that where we're sort of spearheading a new phenomena that's taking the world by storm. So I'm really looking forward to the lecture that we have ahead of us. I'm sure it's going to be brilliant, and also very, you see, we've come a lot further than just putting together simple mathematical pieces that we can then put together. So the lecture that we have ahead of us, and I'll see so that I actually pronounce the entire long title of it right. So we have Yves Klett with us.
Perfect.
And you'll be talking about technical tessellations, origami, aerospace and architecture. Let's see where that will bring us. Please, the floor is yours. Let's give him a hand so that he gets started.
Thank you very much, Dean Valtonen, for the lovely introduction. I couldn't have done it better. Also, my thanks go to Kirsi Peltonen for inviting me to this event. It's a great pleasure and a great honor to be here and to be able to talk to you about technical tessellations. So my name is Yves Klett. I'm from Stuttgart, southern Germany, from the university. I'm working for the Institute of Aircraft Design, that's part of the Aerospace faculty. And I am doing a lot of folding, and I will be telling you about that for about the next hour. I hope it won't be too boring for you. So, to go back quite a bit in time, this is from 1988, so I was still rather small there, but my father dragged us to a paper plane competition. And so my brother and I, we were designing paper planes, and they shouldn't be like, you know, the ordinary paper plane. And so this was the one I came up with. So this is the front. You see it's a bit crumpled, so it saw a lot of action. Anyway, this one, it did fly. It did not fly very well, but it did fly. But for some reason, there was also a design contest, and this plane won the design contest for the juniors. So I was quite happy, and I got this nice picture here, and I think 50 Swiss francs, which at the time was quite a bit of money for me. So at that time, I somehow started doing things in paper, and then, then I went to school and left it off for a time, and now, like, oh dear, 30 years later or something, I'm standing here again, and I'm talking to you about technical tessellations. So what can you expect? No paper planes. I will be talking about some things to do with lightweight construction, because that's where I come from building rockets, planes, and so on. I will try to explain how tessellation design can be done, and then I will show you, don't worry, lots of images of actual hardware, so you see that I'm not just computing stuff, but we're also producing it. And we will have short spotlights on rather very current topics from research we are working on concerning mechanical performance of folded paper, from an example in architecture, and you'll hear about something that is called anamorphic origami. Don't worry, that's the actual entertaining part, so that comes at the end, so you'll all have to stay to the very end to see that. All right, so I'm from the Institut für Flugzeugbau from the University of Stuttgart. We do a lot of lightweight construction, for example, using modern materials, carbon fibers, aramide fibers, plastic-reinforced, fiber-reinforced plastics. We also have model planes, well, rather big model planes. And we also actually build aircraft. So those are two aircrafts that were built at our institute. One is the Icary, and the second one is the Egenius, and I'll explain that second one to you in a short while. And we also deal with wind energy. That's why I like this image so much. So we have a department of wind energy, which is closely related to plane, to aerostructure design, in fact. Anyway, so I'm coming from an institute dealing with lightweight design, aircraft design. So why is lightweight construction important? Well, because planes are not just made for fun, but they are built for a reason. So we want an airplane to have a good performance, we want it to be fast, we want a high payload, lots of passengers paying their fare, and we want a large range. And this has to do with lightweight. The lighter the plane will be, the more passengers you can carry, and so on. And then, of course, there are more things to airplanes. We want to reduce emissions, so we can fly far, but we don't want to burn a lot of fuel for that. And we want to reduce CO2, for example, to save the environment. And, of course, what it all boils down to for the carrier is they want to optimize their margin. But in that case, it's good for the environment. And one way to do this is to build aircraft lighter, but they have to be strong at the same time. So just making it lighter will work up to a point, and then it will not be so good. So we want really strong airplanes, but they should be light. And this also goes for, well, this goes for big airplanes, but also for small airplanes. So this one is the Egenius. I think it's a rather lovely machine. It's for 2 persons, and it was built at our institute. And it competed at the Cafe Green Flight Challenge in California, I think 3 years ago, won the 2nd place for the most economic airplane. And what it does is quite amazing. So you can put 2 passengers in there, and per passengers you need 0.6 liters per 100 kilometers that you're flying. And you're flying at 170 kilometers per hour, so that's pretty fast. So show me the car that can do that, and I'll congratulate you on that. So this is quite a feat, and this was also possible because we used a lot of, well, mostly expensive carbon fiber and built very light. And well, I guess it's the final plane you'll see, but I'm making a point here. So the idea is to get maximum performance of, well, it can be a structure, but it can also be a house or a car or a ship. You want to make the most of the material that you have got. And that does not necessarily mean you always take the most expensive material. You don't always take carbon fiber because this will be not economic, it will be too expensive. But you make the most of what you've got. And the plane I'm showing you here is nice because I'm sitting in there and I'm very happy, but you cannot see me. Anyway, it's got 26.5 meters of span. And this 13 meters on the left, 30 meters on the right, and you really want them to stay where they are during flight. So it has to be light because I have to push it onto the runway, and then it has to be very strong. So how can we go about doing stuff light and strong? And that's where the sandwich principle comes into play. So one of the principles to make the most of the material you've got is the idea of making a sandwich by clever arrangement of material. For example, on the left side, you have 3 layers of cardboard. And on the left side, if you build a bridge like that, it's not going to be a very popular bridge. If you take the same amount of material and put it in a clever configuration, not adding any mass, but just changing the configuration of your material, then you get a material that is well, several magnitudes of order stronger without being heavier, right? So that's something quite astonishing. And I have used corrugated cardboard for a reason, because corrugated cardboard is perhaps the most important sandwich material at the moment for, worldwide commerce. In Europe, we have a yearly production of 42 billion square meters. So in Germany, that's about 120 square meters per person. So that's quite a bit of cardboard. And why is that possible? Because it's very cheap, but at the same time, it is very strong. So you can reuse it, or you can even recycle it. So that's clever use of material. And that does work with cardboard, but of course you can do that with expensive materials as well. And taking the cardboard metaphor is also useful because we are now talking about folded things, or hopefully I will start talking about folded things very soon. And we were searching for core materials for this sandwich configuration. So the idea is to take a light core material and put 2 face sheets on top and on the bottom, and then you get a very strong structure like corrugated cardboard, only much stronger. For example, like this. I'll just pass this through. And there are several materials already available for that, but not all have all the properties that at that time Airbus wanted them to have. For example, just to introduce this one, those are honeycombs. It's a very good material, but it has certain shortcomings, which I'll explain to you very shortly. So we were searching for materials to build lighter airplanes, and we came across this thing called tessellations. So the idea to fold stuff is very old. Origami is Japanese. It means folding ori of kami, paper. So it's rather just means folding of paper, but it sounds very nice. And it's Japanese, so it sounds very sensei. Although it's just folding of paper. And people have been folding paper for a very long time. And folding is a very important industrial manufacturing method. Now, if you, think of your breakfast, right? So maybe you'll drink some tea, so you have a tea bag. This tea bag is folded by a machine. And that's a very special machine, so there's a lot of technology in your folded 1-cent tea bag, for example, or in your newsletter. Or if you start your car, you have like a dozen different filters in there, which are mostly made by folded paper. So folding is very important, but it's mostly unobtrusive. It's not very obvious, okay? So you don't see this oil filter. But without the oil filter, after 50 kilometers, your motor will be, not working as you want it to be. Anyway, there are different ways to fold, and one of these principles is to fold tessellations. And one of the ideas is to take these small unit cells and make bigger structures out of those. And this one is even isometric. That is, if I fold this one, all the blue squares remain squares, and they remain the same size. So what we have here is something that is done without stretching, right? So it's no deformation, and that's useful for a number of reasons. You can use very brittle materials. It doesn't take a lot of energy, so folding is very efficient. And then, if you do it properly, you can combine these small, rather simple unit cells into bigger setups, and you get a structure. And this cellular structure can still be folded from one piece of paper, and you don't need any cuts, and you don't need to glue. So also, another thing that is very useful, because if you have to make a lot of cuts, that takes time, it costs money. Gluing takes time, costs money. So this is the basic idea behind tessellations. There you are. And the one I just passed through is made from aerospace grade paper. So we mostly fold paper, we fold other things as well. But of course there are different grades of paper. So cheap paper and very expensive paper, for example. And so we came across this stuff and we thought that might be useful. And then we tested it and lo, it was useful. So for example, so this is from a small TV spot we made. So we folded like 10 grams or perhaps 20 grams of paper, and we were able to drive a car onto this small sample of fold core sandwich. So you have 20 grams of paper, expensive paper, but paper, and you fold them, and you can put a car on that. So that's not so bad, right? And this is already at a very high performance level. So this kind of performance is actually useful for building lighter aircraft. But that is not the only aspect, because there are already very good materials out there. For example, the honeycombs are very strong. They are sometimes even stronger than the folded cores I presented. But there's an interesting thing in the industry which tries to integrate functionality, more functionality in parts. You want to have a part that is strong, but optimally you would like this part to, you know, for example, distribute warm air as well, or you would like to remove moisture. So you want to integrate functionality. Perhaps you want an aircraft floor that is not just very strong and light, but also functions as ventilation and different things. So the structures, the tessellations I'll show you, have lots of potential for integrating additional functionality, and you can design them to fulfill different functions, and that's a very interesting thing. For example, for an aircraft, it was very important to design a core structure or a sandwich structure which is open to the air, which can be vented or drained. Why is that important? Because in an aircraft, you have the inside and the outside, of course. Outside it's very cold, you have differentials in humidity and temperature and pressure, and that leads to an accumulation of water, for example, in honeycomb structures. And this is something you do not want for a part that cannot be changed. You cannot change the aircraft fuselage, right? Then the aircraft is not usable anymore, and you cannot remove water from 10 million small cells. So we needed to provide a core material that was ventable, because the aircraft has to function for 30 or 40 years. And this was possible using the tessellations, as you can see. So we have these channels. Well, I'll just pass a small tessellation through so you see that as well. And another one for good measure. There you are. So this was interesting. So then the industry said, wow, cool, looks good, you made a good case, now go and produce this stuff. So there we had it. So we needed to produce this stuff. How to design this? How does it even function? Why tessellations? Why isometric stuff? And that's something we also worked on in the workshop, how to design your tessellation. And the basics are quite simple. So you can start with building some basic models, for example, of this Miura Ori. It's called after, not its inventor, but a very prominent researcher, Koryo Miura, who described the structure already in the 1970s. And you can do a bit of analytic geometry. And don't worry, you don't have to do that here, but it's not that complicated. So you just have some relations between the 3D state and the flat state. And that is already sufficient to describe, for example, the kinematic behavior. How does this stuff work? So it's just a few equations, and you can already simulate origami, which is otherwise not always trivial. Anyway, this is kind of a bottom-up approach, so you need probably pencil and paper and some time to write this stuff up, but then it's going to work very nicely. You can also, you know, take it a step further, and I've had quite some time to do that in the last 10 to 12 years. So you can take more complicated folding patterns. So this is a folding pattern. The red things and the blue things are creases, and they are mountain creases, so they will stay up, or they are valley creases, so they will point down. And if you have all the creases fixed, then you can take another bit of math and describe the kinematics of this whole strip of paper. So you know exactly what will happen when you fold this thing without folding it. Well, it does sound less exciting now that I hear it. But this is the strip, so you can also simulate that, so something visual is more useful. And this is the kinematic behavior of this strip of paper. And this is the analytical description. So it's not really very complicated. However, I'm an engineer, and I'll present you, well, an engineering point of view. And so what we usually like to do is we have some CAD system, right? So we have the computer and we draw 3D things, and we want them to work. And that's another approach to design these tessellations. And that's more of a top-down approach. So once you have the software in place, and it takes a few years, you can, for example, write something like this, and it's just some kind of simple user interface where you can manipulate, for example, the shape of this unit cell, or you can fold it and unfold it. Here you see the 3D unit cell. On the right side is the flat pattern you would need to apply to a piece of paper to fold it. And you could do, well, immediately very interesting things. You can change the folding pattern. And you are not necessarily limited to plain structures. If you twist the folding pattern, then you arrive at things that, for example, are like a tube or like a prism. And all of this is done isometrically. So this is pure folding, virtual folding, but pure folding. So you can do this using very brittle materials, for example, aluminum or paper, and it's going to work. And I think the participants of the workshop can prove that I'm telling the truth. Anyway, you can do lots of different things with a piece of paper. And of course, it takes a while to get into the whole thing, but there are many different levels you can design for a structure to fulfill certain functionalities. And one of these levels, and perhaps, well, the most obvious, is this macro level. So what shape should the structure have? Should it be a plane structure? This is very useful for a floor, right? Aircraft floor, or for housing architecture, perhaps. But it's a bit boring. So I want my shape to change thickness. Well, that is possible. So take a piece of paper, do a bit of math, and you can derive the pattern that is necessary to fold this strange thing here. Or you can do something with a curvature. For example, for the aircraft fuselage, that was very important. And is also industrially relevant. And you can combine those. So I want changing curvature and changing height. Hey, how does that work? Well, it works exactly like the more simpler examples before. And it's in this case, not very complicated to actually do it. Folding is something different. And perhaps the most interesting thing here is something with double curvature. Now, curvature is a difficult topic in sandwich for many, many structures because it is not always simple to do something spherical, because the honeycombs, but also the tessellations, will not necessarily, easily fit into a sphere. So I want this to be a sphere. Yeah, so pretty nice sphere I've got here, right? So this is difficult because most core materials have an anti-clastic behavior. And this means that they form a saddle when you try to deform them. And most of the time I don't want it to look like this. I would like it to look like a sphere. And this can be done using proper design. Then there's the second level. So we're moving down one level, and that's the meso level, the medium level. And this concerns, well, I know how my overall shape should look like. How should the cell look like? And this is something where tessellations are really, well, extremely versatile, because you have many things you can design. This is just a tiny slice of possible configurations for a certain macro shape, which is just a flat panel. And you see the slightly differing crease patterns. Well, okay, it does differ somewhat. But if you actually fold these things, they will all fit into the same design space, but they will have completely different properties. For example, mechanical properties, acoustical properties, probably pricing. Of course, the looks will be different, and so on. So, well, you have an infinite design space to choose from. How should my tessellation look like? And at some point, you have to make a useful, well, decision. For industrial products, of course, manufacturing is very important. So most of the time, we stick to the simpler structures. But especially origami hobbyists are doing crazy things with tessellations. So they go wild and work days and days on tessellations. So I come from an industrial background, so usually I try to make them as simple as possible, and then I want some machine to make that for me. And in the meantime, we've managed to do that quite nicely. I'll try to show you some variations. Let's see how long that will take. Some live demo of kinematic simulations of different unit cells. And it just takes a few seconds to start up. In this case, Mathematica, where I program most of my stuff. Yeah, so let's hope that works. No, not really. Yeah, absolutely. Sloppy work, me not starting the kernel in front of this whole thing. Yeah, I'll skip that one and try to make that work at the end of the presentation. However, it's not crucial, but I'll try to show you this because I like the Star Wars origami, and this is what I call the Xylon Death Star origami, so they are closely related. So let's try to make that work. Anyway, so lots of shapes in the meso level, and then we go down one more level, so that's usually the micro level, and there you have it. And so this is an original size paperclip, so it's not a huge, gigantic paperclip, it's a normal paperclip, and you might imagine it's quite hard to fold this small, and yes, it is. And then you have to add all these small holes in there. Why was that done? This was an actual application where we are still researching it, and it's about boundary layer suction. What is that? Well, you have an airplane and you have an airfoil here, and you want to influence the aerodynamics of the air passing this airfoil. And this can be done by something called boundary layer suction, where you actually suck the air into the wing, and then it stays close to the wing, and you can reduce the drag, so the resistance. And this would be very useful for sailplanes, but also for big planes. So this was something we wanted to realize with a folded core structure, which is in there, so it's not very thick. And we have all these little holes, and they have even differing diameters. So that was quite taxing, and all of these holes have to be positioned very precisely, and their diameters have to be also very precise. And this cannot be done after folding. It's impossible. There's no machine that can do that. So the good thing is we can work with flat paper. We can work with, well, any flat material that's available, and there are many of them. And we can work in the flat state, and that's state of the art. You can laser them, you can emboss them, you can print on stuff. I'll show you examples. In fact, you're passing them around. So this is very convenient. Anyway, so this is the micro level. There are many ways to work on the subcell level to make a structure more interesting. So well, you've seen hardware already, but simulating folding is sometimes easy. The first steps are, well, can be taxing, but you know, there's no difference between 1 unit cell and 1 million unit cells, because it's the same. You know, you can just string them together. It's not very interesting, but there's a big difference between 1 unit cell in reality and 1 million unit cells in reality. So it's about 1 gazillion times more difficult to do them. But I'll just show you some hardware so you get an idea what we have been doing for, well, more than 10 years now. There should be some hardware. All right, so this is what a fold core sandwich can look like. For example, this is carbon fiber. These are carbon fiber face sheets on the top and on the bottom. In the middle we have a folded core, and it's quite a fancy one, so we put in this window. The window should not be there usually, but we put in this window because it's so beautiful. And all of this is glued together using a film adhesive. And this is something you might encounter in aerospace. So that's an actual structure that might be useful. And this is a macro image of some of the first panels we managed to produce. It was incredibly hard to produce large panels. And everyone who folded a small tessellation yesterday can attest to that. The idea was the following. We want to make a sandwich fuselage. So this is a section of the fuselage. Of course, it's round. And we have these inner and outer face sheets made from carbon fiber. And in between, we put this nice folded core. And further, the folded core is designed so that the channels all point downwards. So if there is moisture, and there will be moisture, the moisture will drain downwards assisted by gravity. So that was quite an important thing. Sounds like a small detail, but it changed the whole way we had to design the structure. And this is the actual setup by Airbus to, well, use our core and make something useful to test out of it. So that's 4.5 square meters of, well, folded core sandwich in a Vasco test shell. And you can see these rather narrow panels which fit together like a puzzle. So you can just, you know, put multiple panels in, put them together, and you're all set. And the technicians at Airbus were quite happy because we also integrated this radius of 2 meters into these panels, which would otherwise have been quite complicated. So that was a very successful project. As you might imagine, well, working 12 years on a project, we have been folding lots of different tessellation geometries. And, well, after geometry 200 or so, well, I decided I need something of a database to put them in because, you know, it's like a zoo. They tend to get lost and they die and they need to be fixed somewhere. So we have this database where we put all our geometries into. And at the moment we are at number 716, so counting daily. But the interesting thing is that most of these things we did not just design, but actually fold. And I'll show you some examples of that. Why do we need so many different geometries? Because we have lots of different, well, specifications by the customer. I want it to be strong in this direction. No, in this direction. Oh, I want it from aluminum. Oh, no, I want it made from paper, and so on. So about, well, many thousand different wishes from the customer. And then there's a second thing, that is tessellations are very interesting, but they are technically a fairly new thing. So the idea to fold them is quite old. But the actual drive to research them as a high performance, for example, core material is quite new, and that started possibly something like 12, 13 years ago. So there is not yet a lot of information available on this stuff. Also because actually producing it is, well, it can be quite hard. So we put a lot of time into that. Anyway, we've got lots of these thingies. Now, the sad thing about the whole tessellation business at my institute is that usually we go and hide them, all right? So here's your tessellations, I'm so proud. Yeah, okay, so let's put on face sheets and glue them together, and then let's destroy it, okay? So that's kind of depressing if you spend a lot of time manufacturing them. And I think for an inspiration in the direction of art and design, it is more interesting to have a look between the face sheets and show you the actual tessellations, because any sandwich I will show you will more or less look like this, right? So that would be quite boring, not for the mechanic, but for you. So let's show the inside of lots of things we have done. So this is a tessellation that is folded from aluminum. Because we fold isometrically, well, more or less isometrically, of course, at the edges there will be some stress and some deformation and plastic deformation. But because in general we do not deal a lot of deformation to the material, we can fold stuff that is otherwise very fragile and brittle. And aluminum works very well. What also works very well is the yellow paper I passed around. This is a very expensive paper. It's made from Kevlar fibers, which is an aramide fiber, so it's used for, well, fireproof clothing and ballistic protection and so on. But this paper is very expensive, but it's used for high grade, for aerospace grade core materials, for honeycombs, for example. So, and this is also a nice tessellation, I think, so it's just to show you not everything looks the same. And this might look strange. What this actually is a carbon fiber mesh. So for some reason, a colleague of mine decided, hey, I've got this strange carbon fiber mesh. How about you fold it? And said, oh, yeah, of course, let's fold it. So we spent some time to fold that, and it worked rather well. But the interesting thing about this is that it's also a proof that the folding process is very gentle. Why? Carbon fibers are very strong, but they're extremely brittle, so they do not take kindly to deformation. And so this is the actual proof that we have less than, for example, 1% of deformation or 1% of strain, because otherwise we'd have lots of very ugly carbon fiber confetti, and we don't have that, so it works. But you can use, well, just about any material you can imagine, which is not, well, probably, a sheet of glass will be difficult, depends on the temperature though, but you can fold lots of things if they are thin enough. And this is thermoplastic material, it's polycarbonate, it's colored, and it has this nice effect that the creases break the light, so you see the creases very distinctly, and I think it's quite nice. So unfortunately, I didn't bring that material here. We are thinking of lampshades and different things. This is just another tessellation, also, well, a rather small one. This is a Swiss franc. It's much more worth now than when I took the picture. I'll have to search for it. And then there's an interesting thing called curved fold. So that's a very hot topic in the origami community at the moment. Because it turns out, if you want to fold something, you don't necessarily need these sharp creases. You can also use curves. And what results is a very gentle, way of folding, and it has many interesting properties. I'll get into that very shortly in a few minutes. And it also looks brilliant, I think. So this is also something for designers. There is a British company called Robofold, which does curved folding of metal sheets for architectural applications. So they do, things like rather large curved folded scales for buildings, etc. So that is very nice. And then we are not limited to plain structures. So, wow, I think it's actually the same thing I'm showing you. It's more pretty on the picture, but this is some kind of tubular core. And again, this would be rather difficult to manufacture or, to build with other core materials. If you take a foam, you would have to thermoform it. If you take honeycombs, you would need to use a special kind of honeycomb. Or you would need to use lots of small pieces of honeycombs in the right shape. And that's not very convenient. And this is something else. So this is something that we designed for a filtration application. So I was talking about filters, and filters are, there are billions of filters out there, and most of them are just folded from special, filtration paper. And this was something that should work as a filter, and it was also very flexible. So that was a very interesting cooperation with the filtration industry. This might be interesting because I'm talking a lot about sandwich applications, but of course, tessellations are in no way limited as a core material. You can do everything you want with a tessellation, right? You can do design, you can do technical stuff. Excuse me. You can do it for fun, and I would recommend that you do some for fun, and the rest for business. Anyway, and this is so you can also use any kind of plastic. So this is clear plastic, and there are lots of tiny holes in there. So this was for an acoustic application, and I hope that this will be successful in the short future. So just to show you a few examples of tessellations we did. I'll pass around the aluminium one. It's rather nice. This one was actually folded by a machine, so no hands involved. And of course, it's much more convenient for me or for the students that usually have to do all the folding. I'll go briefly into mechanical performance. I introduced lots of different unit cells, okay? So you can use lots of different unit cells to generate a structure that will fill a given volume. And this is a very current research I presented last year in Tokyo at the 6 OSMI conference. This is a comparison of mechanical properties of these 7 unit cell types. Don't worry, it's not very complicated. So we have, for example, samples folded with this unit cell, this, or this unit cell, and we get these small, for example, samples like this. And then we have 3 more. So this is a curve fold, this is another curve fold, and this is a water bomb fold. And what we did is we put them in a sandwich configuration, that is, we put them between 2 face sheets, and then we compressed them with a machine. So actually we destroyed them, which wasn't too bad because those were easy to make. But you put pressure on them, and then you measure how strong are they, and what is their modulus? That is, how much resistance do you encounter while compressing, right? And for example, it looks like this. We put them between these acrylic face sheets, and then we put them in a testing machine, a rather violent setup. So here they are, and we start compressing, right? So at the moment, everything is groovy, and then we start to compress, and something is happening with the structure, right? So this is something you might not want to encounter in real life, but in testing, yes. And okay, so this structure will not stand up again. So this is destroyed. But that's okay, because we want to know how much can this thing take. It's a crash test for structures. And then you can measure, for example, the strength. So at which point will it collapse? And you can measure the modulus. That is, how much force does cause how much deformation. And the interesting thing is that the shape of the unit cell influences the mechanical properties very much. So, on the left side, this rather boring straight fold is not really very good if you compare it to the others. Numbers 2, 3, and 4 are not so bad. It goes up and down. We don't know exactly why, we have theories. And now it gets interesting because there are these new curved folds, which are really quite new because they're devilishly difficult to produce. And all of a sudden, we have something that is more than 40% better than all the stuff we tested before. Okay, so now I've been folding for 8 years, and now you come along and tell me, oh, but I can do 40% more. Yeah, it's like that. So good things happen. And then the last one was not so good too, but it was interesting for other reasons. But just to show you, the meso level, for example, influences the properties of a structure in a large way. It's essential. So you cannot take anything and try to build anything with that. You really have to take care what you are doing. But that's also, well, a nice thing about tessellations. You can do things. So if you want the maximum compression performance, I'd go with number 6 in that case. This is this is a similar diagram for the, oh no, it's the same diagram. Yeah, right, sorry, I was talking about, so this was stiffness. Please excuse my mistake. So this was stiffness, and this is strength. And it's even worse here. So we have the number 1, bad, 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 and then it stays on a certain level. And then number 6 goes up like bam, and it's better than all the rest. And why have we not folded like this for the last 10 years? Well, we didn't know, and well, the others didn't too, so that's okay. But it's important to know your stuff at some point. And so much for mechanical performance, because that's what we mostly deal in. Architecture is, of course, very interesting, and architects seem to like folded structures. There are many examples of them. I'd like to present one we realized using fold core technology. This is the Stuttgart Smart Shell. It's a nice wooden shell realized by an institute of our university, and it's a very thin shell. It's an active shell, so the foot points can move and the structure can equalize tensions on the surface. So it's a very interesting concept. And the architects came to us and said, all right, so why not do that in sandwich? And we said, well, oh dear, what are we doing? And well, after 1 year of hard work, we managed to do a small scale thing. It's 1 to 2.5 scale. So it's 4 by 4 meters, and it's all made up by fold core sandwich. It's got quite a number of creases, more than 300,000 creases, all folded with dear assistance of many, many students. So it's good they are cheap and very talented, of course, so don't worry. They got a good deal out of that. Anyway, it's probably the biggest fold core sandwich piece in the world. It's in Stuttgart. And the nice thing is that it's a double curved shell, right? So we have double curvature. And this is something that is not easy to realize with standard core materials. So you see, I repeat that many times over because it was a lot of hard work to do that one. And I think the result is quite stunning. It's very light, it's strong, and, well, lots of creases. Some details. It's also active, so we have all these gizmos in there which move the structure and pull on the structure and so on. That was all done by partner institutes, so we just made the structure. But we also demonstrated other things. So, wow, we've got this shell that's got 1,000 channels, so we need some current here. We need cables. Oh, where are we going to put the cables? Well, it's kind of obvious. We put them in the channels. And that was very useful because we don't have to do extra work to integrate cabling. And each of these quarter shell pieces weighs about 25 kilos. Embarrassingly, most of that is glue, but that is due to other reasons. So we have about 3 kilos of core, and that accounts for a very strong structure. Oh, Nice picture one more time. This is the cross section. So we have glass fiber face sheets and the core in between. And then there's glue to, well, connect these 3 pieces into a high-performance sandwich. And you can see the cabling. And now, if you look closely, you also see that you will need quite a bit more cabling than if you were using a straight line, but usually that's not a problem. Anyway, it might look like this, but that's not deciding. So that was a very interesting architecturally related project we did. We also did workshops with architects, and usually architects are after, well, not the closed sandwich because that's boring and you can buy that, but they want to work with shapes and geometry. And of course that's much more fun than doing mechanical stuff. So the next spotlight will be on anamorphic origami, or in short, anamori. So this deals with anamorphosis, and what is that? So anamorphosis is a distorted perspective which can only be deciphered using either a special point of view or a special viewing device. So in this case, the viewing device is a reflective cylinder, and this is the anamorphic drawing. And if you look from one point and one point only, then you'll see, oh, it's a lovely image of children playing with a ball. So this is an interesting concept. It's been around since the early Renaissance, used by many painters, and it's an interesting concept. And it's also, well, super for street art. So there are people going around doing chalk drawings like this, and you think, wow, it's a waterfall, but no, it's not, because the guy is just walking here. So this is just the street, and it's just been painted very cleverly. And it evokes the illusion of something three-dimensional, of something that's not actually there. And you should Google for that. It's pretty amazing. And you can apply this concept of anamorphosis also to tessellations. So if you take a tessellation and you decide to color each face in a different color, well, at the unit cell level, and then you make a big tessellation using a periodical coloring. Oh, here we go. So we make a big panel out of this. Then all of a sudden you have a structure that is quite, well, funny to look at, right? So because depending on your viewpoint and your position, although the coloring is uniform, you get either, for example, a mixed color impression or something darker. So you get a continuous mix of colors, and you can imagine having a wall like that, walking around, and then what's that, and so what. So this, I think this will be fun realizing something big in architecture, where you change your viewpoint and the structure really changes its appearance. And we can do this for many, well, for every tessellation, and there are so many tessellations. So this is a two-color example of a slightly different tessellation. Again, let's make a, so that's the flat pattern. Looks a bit asymmetric, and it is. So let's make a big one, big E, and let's fold that. Yeah, here we go. And this is a somewhat asymmetric structure. So if you look at it from the top, it's just plain yellow. And then in a very narrow angle, it's all red. So the change in color is very, very acute and happens very fast. And sometimes it's also mixed. So it depends really on your point of view. And you can do this very simply using a, well, printed sheet of paper and folding that. So this is the mock-up of the four-colored, well, it's not the mock-up, it's the realization of the four-colored thing. I'll try to, I'm not sure if this is working, but I'll try to give you different viewpoints and impressions of the structure. So the change is rather interesting, I think. Again, four colors may be a bit much. I have one in my sleeping room, and sometimes it's a bit, you know, exciting. Oh, all those colors. But I usually dream quite nicely, so it's okay. And it's dirt cheap, excuse my French. It's dirt cheap, so you need a printer or a, well, color pen, and you color your origami, and then you have an anamorphic origami piece, which can be quite interesting. The thing I passed around actually is also just done that way, so it's printed and then it's folded. The next one is fun. Oh, sorry, I was too fast. So this one is fun because the structure, let's try that one more time. So this is a circular setup. This is the unit cell. Let's make, this is the unit cell developed. Let's make a cylinder out of that. Okay, a few unit cells, and then let's make a long cylinder out of that. And so it's mixed impression, but now the inside is yellow, outside is blue. And if you turn that over 180 degrees, surprise, surprise, you may already imagine, the inside is blue and the outside is yellow. So not half bad for a, well, 2-penny structure. So you can do interesting things. And it becomes even more fun, if that is even possible, if you use not a discrete coloring, but if you use textures, so if you use complex images. For example, a checkerboard pattern. Now, to see the checkerboard pattern in 3D, you need to print a distorted version of the checkerboard pattern in 2D. But that, in fact, is a very nice application of some basic affine geometry, so it's pretty good for bringing this concept across in the classroom. I would say, I'm not sure, I haven't tried it, but it should be, so teachers beware. So this is nice, and of course the checkerboard pattern is boring, but we can use a more interesting, well, more fun image. So hello Bender, and as you might imagine, Bender is, well, caught on a Miura-Ori tessellation, so you can only see him properly from a top point of view, in this case. And to actually fold this thing, or to actually fold this thing, oh, I wanted to use this, but I think I'll skip, you've seen that. You need to prepare this flat pattern. So the distorted flat pattern is printed, and then it's folded. You can try with this one if you want to, so you can put it flat. We can put it back together, it's reversible. And you see it's not entirely, well, intuitive how the actual image is distorted. And then we can, well, we are not limited to flat, simple tessellations. Let's take a curved thing. So this is a mystery tessellation, and all we see is a checkerboard. Well, yes, it is. And now you can try to guess what structure is behind this thing. Of course, I removed the lighting, so it's quite difficult, but this is a set of reflected cones. It's quite simple to fold, actually. It's just a sector of some concentric circles. And this is the flat thing you would have to print out and fold to realize at this anamorphic checkerboard, whoa, conical thingy. So it's not that difficult. And of course, you can go completely wild. So we have Bender again, but this time he is on a mystery structure, and it's not flat and it's not conical. In fact, it's something, well, screwish, I would say. This is still a tessellation that you can fold using a long strip of paper and a bit of patience. Actually, the folding is completely trivial. Only the deriving of the folded strip might take a few years to, well, for the first time. Did for me. And then we can unfold it. Right, so we do a bit of simulation, and we unfold it, and yeah, now it looks weird. And of course, Bender is going round and round and round, but in the end, we get this long strip of rather strangely, well, patterned paper, which again, if refolded, will result in this anamorphic thing. And we are working on, well, producing some hardware, some bigger hardware, because simulation is easy, but the cool thing is to actually see the stuff. You can look at this later on, of course. And finally, just to, well, to come to a nice end, of course, origami is an extremely well-suited topic for education, and education on all levels. Why? Because it can be simple, but it can also be as complex as you want it to be. And then it is very cheap. So all you need is a piece of paper and a pen and a ruler, whatever. You can spend, well, you can spend millions of money on equipment, we do, but you can work with a piece of paper, it's okay. You can start like that and, you know, work up, but it's very cheap and you can do it on the spot. And there are many, many different aspects to origami. Kirsi and I discussed this at lunch. So you can do, well, you can start with basic trigonometry, but you can, well, you get very quickly into, well, high-end mathematics territory. So differential geometry is just, well, it's just one of the simpler things you can get into. So there's lots of things to be done in origami, and the good thing is, well, to relax you can always do some practical exercises, and that's integral. And this works on all levels. Truly, I tried them all. So we had this big fair going on, and we had a few thousand kids folding their own piece of sandwich using a simple template costing about 1 cent. And they put it between two cardboard face sheets. Actually, those were beer mats, but no beer advertisements on them, just, you know, vanilla beer mats. And you can see the little pieces, and, well, you can perhaps imagine the children are just, well, they are really concentrated and they work very precisely. So it's extremely cool, up to the point where the parents decide they know better how to do it, and then it becomes, you know, a drama. But for children it's great. And then for students it's, well, also great. So this is a picture from a workshop I had the pleasure of giving in Innsbruck, and you recognize Miura Ori and a Hypar and the water bomb. And so students really can identify with origami. Those were architecture students, so they like geometry, mostly, if it works. And then you can also spend money on this thing, and you can do like professional courses. And this is a workshop I gave together with Rupert Malecek in Berlin 2 years ago. That was a very good workshop, and those were, well, mostly professional architects from high-end, well, companies. We folded nifty things, folded curves, curve folds and other things. And most of them are still smiling at the end, right? So it couldn't have been that bad. And then this is a nice video. So this is a piece one of the students did in Innsbruck. I think it was an umbrella of some kind. And we all helped folding it together, because tessellations are sometimes tricky. You have to make every crease point in the right direction, and then it comes together very quickly, so that's a gratifying part. So you can see we've done all the work, and now it's just pushing it together. Right, and there you have it. It's flat foldable. And just look at the faces, right? So just take a look at the face. Yeah! Oh, look at this. Ooh, it's done. Okay. Ooh. Right, so. And yeah, so he's quite happy. Oh, and every time when I'm thinking if I'm being too harsh to my students, I take out this picture, I look at his facial expression of total zen, and I think, no, they can do it. So it's quite cool. And essentially, this was already most of the talk, and I'll recap very, very shortly. So origami and folding is not just child's play. It is very important in an industrial context as well, in a well-designed context. But it is also a lot of fun, so that's a good thing. And there are many, many useful applications. Go into your local supermarket, look at the packaging. Sometimes it's very intricate. People are earning money with that, so there's money to be made and fun to be had. And the good thing is, most of the things possible have, per definition, not been discovered yet. So it's a wide open field. So there's still enough white space on the map for all of you to mark your territory and to do new cool things with origami. So that is really a plus. So in research, origami is super hot, and more or less everything you do hasn't been done before. So that's a good thing. And well, with that, I'm mostly at the end. I would like to thank you very much for your attention. I'd like to excuse the not functioning demo, but I'll be happy to show that later on. And if you have any questions, hit me, please. That's the most interesting part for me because I know the rest already. Thank you very much.
Thank you, Yves. It's not after every lecture that we know how to reach total zen, nor what to do with our students. So now we know all of that. Any question? Who wants to dare to shoot first? I'm sure it's opened a lot of thought. Great. Do you want me to do the running, or can we get some? Great.
Hi, your examples were mostly about structures.
Right.
Have you been, or anyone at your university, working with packing problems?
Funny enough, not from a packaging point of view. There's this big topic in origami, and that's deployable structures. So that is all about things that need to be big, but somehow they need to be small for transport as well. So think solar sails, or solar panels for satellites. So there's quite a bit of research going on in that area. We don't do a lot of deploying structures, and we haven't actually done packaging design, no. So no one's come up to me yet. So not yet, no. So I do it, for Christmas. We do nice Christmas cards. They're pretty hot. But we haven't been paid for that yet, so I'm looking forward to contact. And this should be a really fun thing, because if you go into the supermarket, and I saw also in Aalto University, there were many nice examples of packaging design which have to do, well, because paper is packaging, right? So, and paper is folding, so everything you see in the supermarket is folded, and it's the way to go. And there are some nifty things. I think, for example, the anamorphic thing might be cool for packaging, because if you walk by, this aisle, and it's, oh, it was green, no, it's red, and it's like, oh, let's go back. And it might be a quite heinous way of, catching the attention of the potential buyer. So that might be interesting.
And a wonderful analog way of doing it as well, because that's what everyone is working on at the moment with digital solutions. So
yeah,
you can actually do it by folding. Great question. More? I can see all your brains are buzzing. Here's one.
Yeah, don't worry. I'm happy to answer simple questions too. So that's not...
So yeah, I was just wondering that in real life applications, usually stuff gets broken.
Yeah.
And in normal honeycomb, it's already quite difficult to repair. So I was wondering, especially these really weird looking origami things are probably really difficult too. So have you studied this area at all?
Yes, in depth. So this is a very good point. For an aircraft, repairing is essential, right? So if someone drives his forklift into the side of the airplane, you don't throw away the whole airplane. You have to repair it. And, well, it happens all the time. That happens all the time. And with metal, this is a well-proven technology. With sandwich, as presented for the Airbus project, for example, it was a major thing to work on repairing technologies, or repair technologies to make that work, because sandwich is by nature more complex than a monolithic way to build structures. So aluminum would be monolithic, right? So you have one piece of aluminum, but in a sandwich shell you have two face sheets and a core, and then you have the glue in between, so that's complex. And repairing is much more, well, not difficult, but it takes much more work than for the aluminum, because with aluminum you put a patch of aluminum over there, a few rivets and you're all set. But for the sandwich, you have to take proper care that everything's done properly, and carbon fibers are quite, a very ambitious material. You have to do it properly, it has to be clean, and so on. So yes, repairing is much more work-intensive than for metal structures, but there's no big difference between different core materials. So if you take honeycombs and folded cores, the amount of work for repair would be about the same. And you can do it, but it's it will be more expensive than for a state-of-the-art metal airplane. So that's also the case for current aircraft using carbon fibers. So repairing a Dreamliner is much more expensive than repairing your 737 or a 320 or something. Well, that's a very good question. And it's like we have whole dissertations on the topic of repair. So big topic, lots of effort going into that.
Good, so now I know what you can do dissertations on as well.
Absolutely.
Good.
So I did my dissertation on, well, folding structures, not surprisingly, and we've got them all lined up, so we keep them coming, so that's a good thing.
So we can stand on the shoulders of people before us.
So
more questions coming up.
It is, even if I say it, it is proper science, so.
Yeah, next one, please.
Hello, I'm quite interested in this foldable structure. So origami is a foldable structure that means it can move from one state to the other.
Yes.
Which means that it can move. So that I wonder if there is some research about this kinematics of foldable structure.
Absolutely, yeah. That's.
Or if you have any insight about this kinematics, can you
Yes.
explain a bit?
I didn't put the slides in there for, well, timing reasons mostly. Yes, so I mostly presented origami tessellations by means of looking at, well, core material. But origami is, of course, in most cases, it isn't a core, but it is always a mechanism. So folding is a mechanism, and I didn't mention that, but for example, this structure has another property. So it has only one kinematic degree of freedom. It's a 1 degree of freedom structure, mobility 1. So it has only one possibility to move, right? If I move this point and this point, the rest of the movement is prescribed. And this is a very interesting property for many applications. And there is a whole area of research concerning origami mechanisms, because they are useful in many applications. Well, the simplest is, well, a tea bag or a newspaper, so it's folded and you can refold it. And the more ambitious ones are, for example, solar sails. So there are different projects on how can I fold stuff so that it packs very small, and then it has to deploy, for example, in space, and we need this solar sail to deploy, and this should really deploy, you know? I mean, if the solar sail doesn't deploy, so this solar sail thing will not really work. So it has to work. Or a satellite solar panel, this one has to work. If it doesn't work, the satellite is just scrap, so scrap $20 million. And there are many interesting things also concerning vehicles, and if you look for it in the internet, there's things like micro drones, which look like small dragonflies, and they are produced using origami principles and origami mechanisms. So that's a very active research. We do a bit of that. In fact, it's something of a side product of the whole origami simulation, because I want to build very precisely, so I need to know how it's going to fold. And of course, the byproduct is I know how it's going to move from this state to this state. And now the interesting way is to identify applications where I need things to move from here to there, perhaps going by here and so on, and to realize that in an interesting fashion. Another interesting example, that was on the internet quite a bit, there's an origami pop-up microscope that was quite popular, because it was a pop-up thing, and you can, for a few cents, generate this microscope setup, and you just need one lens, and you put it in there. That's very clever. So starting with children's books, there's lots of pop-up folding, going up to, well, the crash absorbers in cars are under-researched. They might benefit from being manufactured using origami, well, paradigms and so on. So it's a big topic, yes. Absolutely. And if you can, there's a lot of research on the internet. So if something interests you, try to Google origami and whatever interests you. And someone has probably already thought of it. Don't worry, they haven't fixed it yet. So thank you, it's a good question.
Great, more questions.
As an artist, have you had any art exhibitions of like this kind of art? Yeah.
This is, in fact, a tricky question because being an engineer, I'm probably not qualified to talk about whether something is art or not. So I enjoy many of the things I do, and I have to mention, of course, it's not my personal project. We are a whole team working on folded structures, and it's been a joint effort. But so we get into dangerous territory if we start doing art, because then someone is going to ask, well, what did I pay you for? So no, we haven't done large-scale exhibits. So I've given these workshops to architects, and for example, in Innsbruck, the students made very cool projects like the shade and other things. And most of the stuff I've done for fun purposes is hanging in my flat, or sometimes in the institute, but most of the time it hasn't been done with the intent of producing art. I can only hope that at some point something's gonna come out that other people like and might term art, I don't know. But probably the next thing is going to be large-scale anamorphy. So I think this should be really cool, fun, easy to produce, and then someone has to come along and say, oh, I think this is art, and then perhaps I get a badge, and that would be cool.
I think there's also, the one thing about doing art yourself, the other one is inspiring other people to actually do something out of it. So I think listening to you today and hoping for all the workshops that will be following, I can already see quite a few heads buzzing, and I'm sure that, you know, all the things that you've shown us today will be very inspiring for the people who attend the workshops, and maybe out of that. So maybe that's also part of the idea of the Aalto University, that not one individual needs to be the engineer and the artist and the businessman and everything in one, but you can actually work in a team where you come up with these great structures.
Absolutely.
Collectively, we can take them into the next plane.
It really does work both ways. So this is really very fruitful. So I've had contacts with architects that only started like 3 years ago when they invited me, and I had an architectural point of view up to that point, and I still have no clue about architecture, but I came to understand them, and I understand, okay, that's what they would like, and so it goes both ways. I learned about, filtration, I learned about architecture. Filtration is interesting, but I learned about architecture, I learned about art, about design, and it's a very gratifying experience. And I try to show some basic stuff, and then people usually go wild and they do stuff, and I say, oh dearie, that should work, I have no clue, I'm quite afraid if this is going to be a good idea, and then it works out and it's brilliant. So go ahead and try this, because you can't do wrong in that case. So worst thing will happen is that you need a new piece of paper. That's cheap.
And this is a very inspiring discussion as well. I can see it would be continuing for a long time, but I have a suggestion. What about we take it more informal, and that we continue the discussion? Yves has promised to be here with us for a short moment at least. So
sure, absolutely.
So you'll be here to be easier to approach rather than with a microphone, if that's daunting to you. And if I understand correctly, there might actually be an opportunity to do that in a very Finnish way, and that's over coffee, which will be...
I thought in sauna.
Well, you know, wait till you get there. You know, it will take you a few cups more of coffee first. But so that's what we're going to do next. We're going to first thank you greatly for a wonderful lecture. Let's give him the second big hand of today.
Thank you very much. Thank you.
And then let's all continue the discussion together over a cup of coffee outside. Thank you.
Thank you very much.